Lecture 1. Electronegativity. Electronegativity is one of the most important ideas in chemical bonding. It tells us how strongly an atom attracts the shared electrons in a covalent bond. The key phrase here is shared electrons. We are not talking about electrons that belong to one isolated atom. We are talking about the pair of electrons sitting between two bonded atoms. Look at the bond between hydrogen and fluorine. Hydrogen and fluorine share a pair of electrons, so they form a covalent bond. But they do not pull on those electrons equally. Fluorine is much more electronegative than hydrogen. That means fluorine pulls the shared electron pair closer to itself. Because the electrons spend more time near fluorine, fluorine becomes slightly negative. Hydrogen, which has less electron density around it, becomes slightly positive. So electronegativity helps us understand why some bonds are perfectly even, while other bonds have one side that is more negative and one side that is more positive. The simple rule is this: the more electronegative atom pulls harder on the bonding electrons. That one idea will help us understand nonpolar covalent bonds, polar covalent bonds, ionic character, and even some trends in bond strength. Lecture 2. Electronegativity across a period. Across a period, electronegativity increases from left to right. Let's use the second period as an example. Lithium, beryllium, boron, carbon, nitrogen, oxygen, and fluorine. As we move from lithium to fluorine, the number of protons in the nucleus increases. More protons means the nucleus has a stronger positive charge. Because electrons are negative, they are attracted more strongly to a nucleus with more positive charge. This stronger pull from the nucleus is called a higher effective nuclear charge. At the same time, the atomic radius generally decreases across a period. The outer electrons are pulled closer to the nucleus. So there are two important things happening together. First, the nucleus is becoming more positively charged. Second, the bonding electrons are closer to the nucleus. Because of this, the atom can pull more strongly on electrons in a covalent bond. That is why fluorine is much more electronegative than lithium. Lithium has a weaker pull on bonding electrons. Fluorine has a very strong pull. So the trend is clear. Across a period, electronegativity increases because effective nuclear charge increases and atomic radius decreases. Lecture 3. Electronegativity down a group. Down a group, electronegativity decreases. Now look at lithium, sodium, and potassium. These elements are in the same group, but as we move down the group, each atom has more energy levels. Lithium is small, sodium is larger, potassium is even larger. As the atom gets larger, the valence electrons are farther away from the nucleus. And there is another important effect: shielding. Inner electrons sit between the nucleus and the outer electrons. These inner electrons reduce the attraction between the nucleus and the bonding electrons. So even though potassium has more protons than lithium, its outer electrons are much farther from the nucleus and much more shielded. That means the nucleus cannot pull as strongly on a shared pair of electrons in a bond. This is why electronegativity decreases down a group. The atom becomes larger, shielding increases. The attraction for bonding electrons becomes weaker. So the trend is down a group. Electronegativity decreases because distance and shielding reduce the pull of the nucleus. Lecture 4. The Pauling scale. The Pauling scale gives us numbers for electronegativity. These numbers help us compare how strongly different atoms attract shared electrons. A higher Pauling value means the atom pulls more strongly on bonding electrons. A lower Pauling value means the atom pulls less strongly. For example, fluorine has an electronegativity value of about 4.0. That is the highest value on the Pauling scale. Oxygen is also very high, around 3.5. Nitrogen is around 3.0. Carbon is around 2.5. Hydrogen is about 2.1. Elements like lithium, sodium, and magnesium have much lower values. This is useful because we can compare two atoms in a bond. If the two atoms have very similar electronegativity values, the electrons are shared almost equally. If one atom has a much higher electronegativity value, the electrons are pulled toward that atom. And if the difference is very large, the bond may have strong ionic character. So the Pauling scale is not just a list of numbers. It is a tool for predicting how electrons behave inside a bond. Lecture 5. Electron pull in a bond. Now let's apply electronegativity to a real molecule. Fluoromethane, CH3F. In this molecule, carbon is bonded to 3 hydrogen atoms and 1 fluorine atom. The important bond here is the carbon-fluorine bond. Carbon and fluorine share electrons, so this is a covalent bond. But fluorine is more electronegative than carbon. That means fluorine pulls the shared electron pair closer to itself. The electrons are still shared, but they are not shared evenly. Instead of sitting exactly in the middle of carbon and fluorine, the electron density shifts toward fluorine. This creates an uneven distribution of charge. The fluorine side becomes slightly negative because it has more electron density. The carbon side becomes slightly positive because it has less electron density. This is what we mean when we say a bond is polar. A polar bond does not mean the electrons are completely transferred. It means the electrons are shared unequally. So in the carbon-fluorine bond, the key idea is fluorine pulls electron density toward itself because fluorine is more electronegative. Lecture 6. How covalent bonds form. Covalent bonds form when atoms share electrons. This usually happens between nonmetal atoms. Let's look at chlorine. A chlorine atom has 7 valence electrons. That means it needs 1 more electron to have a full outer shell. If 2 chlorine atoms come together, each chlorine atom can contribute 1 electron to a shared pair. That shared pair sits between the 2 chlorine atoms. Now, each chlorine atom can count that shared pair as part of its outer shell. So instead of each chlorine atom being short 1 electron, both atoms become more stable by sharing. This forms Cl2 chlorine gas. The bond between the 2 chlorine atoms is a single covalent bond because only 1 pair of electrons is shared. This is different from ionic bonding. In ionic bonding, electrons are transferred from one atom to another. But in covalent bonding, electrons are shared between atoms. So the main idea is covalent bonds form when nonmetal atoms share electron pairs to achieve a full outer shell. Lecture 7. Single, double, and triple bonds. Covalent bonds can involve different numbers of shared electron pairs. A single bond has 1 shared pair of electrons. For example, in H2, 2 hydrogen atoms share 1 pair of electrons. We write this as H single bond H. A double bond has 2 shared pairs of electrons. For example, in O2, 2 oxygen atoms share 2 pairs of electrons. We write this as O double bond O. A triple bond has 3 shared pairs of electrons. For example, in N2, 2 nitrogen atoms share 3 pairs of electrons. We write this as N triple bond N. The number of shared electron pairs determines the bond type. 1 shared pair means single bond. 2 shared pairs means double bond. 3 shared pairs means triple bond. In general, when more pairs of electrons are shared, the bond becomes stronger. Also, the atoms are held closer together, so the bond length generally becomes shorter from single to double to triple bonds. So the main idea is simple. Single, double, and triple bonds are all covalent bonds, but they differ by the number of electron pairs being shared. Lecture 8. Nonpolar covalent bonds. A nonpolar covalent bond forms when electrons are shared equally or almost equally. This happens when the 2 atoms have the same electronegativity or very similar electronegativity. A good example is Cl2. Both atoms are chlorine atoms. Because they are the same element, they have the same electronegativity. So both chlorine atoms pull on the shared electron pair with equal strength. The electron pair stays centered between the 2 atoms. There is no side that becomes more negative, and there is no side that becomes more positive. That means no significant dipole forms. In many basic chemistry courses, if the electronegativity difference is less than 0.4, the bond is treated as nonpolar covalent. Examples include H2, Cl2, and N2. In each case, the atoms share electrons evenly. So the key idea is, a nonpolar covalent bond has equal or nearly equal sharing of electrons. Lecture 9. Polar covalent bonds. A polar covalent bond forms when electrons are shared unequally. Hydrogen fluoride, HF, is a strong example. Hydrogen and fluorine are both nonmetals, so they share electrons in a covalent bond, but fluorine is much more electronegative than hydrogen. That means fluorine pulls the shared electron pair closer to itself. The electrons do not stay centered between hydrogen and fluorine. They spend more time near fluorine. Because fluorine has more electron density, fluorine becomes delta negative. Because hydrogen has less electron density, hydrogen becomes delta positive. This creates a dipole. A dipole means there is a separation of charge within the bond. One side is slightly positive and the other side is slightly negative. A polar covalent bond is still covalent because the electrons are still shared, but the sharing is unequal. A useful range is this. If delta En is between 0.4 and 2.0, the bond is often classified as polar covalent. So the key idea is, polar covalent bonds share electrons unequally because one atom is more electronegative than the other. Lecture 10. Ionic Character. Bonding is not always just one category. It is useful to think of bonding as a spectrum. On one side, we have nonpolar covalent bonds. In nonpolar covalent bonds, electrons are shared equally. For example, Cl single bond Cl has equal sharing because both atoms are chlorine. In the middle, we have polar covalent bonds. In polar covalent bonds, electrons are shared unequally. For example, in HF, fluorine pulls the electrons more strongly than hydrogen. So H becomes delta positive and F becomes delta negative. On the other side, we have ionic bonding. In ionic bonding, electrons are transferred, not just shared unequally. For example, sodium can lose an electron to become Na+, and chlorine can gain an electron to become Cl-. The larger the electronegativity difference, the more ionic character the bond has. Polar covalent bonds already have some ionic character because one atom has partial positive charge and the other has partial negative charge. But when the electronegativity difference becomes very large, the electron transfer becomes much more complete and the bond becomes ionic. So the main idea is, as delta En increases, ionic character increases. Lecture 11. Ionic versus covalent. Ionic and covalent compounds are different because the bonding is different. In ionic compounds, electrons are transferred. Usually, ionic compounds form between a metal and a non-metal. The metal loses electrons and becomes a positive ion. The non-metal gains electrons and becomes a negative ion. These positive and negative ions attract each other and form an ionic lattice. Sodium chloride, NaCl, is a common example. Ionic compounds usually have high melting points because the attractions between ions are strong. They can conduct electricity when molten or dissolved in water because the ions are free to move. Covalent compounds are different. Covalent compounds usually form between nonmetals. Instead of transferring electrons, the atoms share electrons. This often forms molecules like CO2 or H2O. Covalent compounds generally have lower melting points than ionic compounds. They are usually poor electrical conductors because they do not contain freely moving ions. So the key difference is, ionic bonding involves electron transfer. Covalent bonding involves electron sharing. Because the bonding is different, the physical properties are different too. Lecture 12. Metallic bonding. Metallic bonding happens in metallic solids. In a metallic solid, metal atoms are arranged in a regular pattern called a lattice. The metal atoms lose control of some of their valence electrons. These valence electrons do not belong to just one atom anymore. Instead, they are delocalized. That means they can move throughout the whole solid. So we can imagine a metallic solid as positive metal ions surrounded by a sea of mobile electrons. This explains many properties of metals. Metals conduct electricity because the delocalized electrons are free to move and carry charge. Metals are malleable because layers of metal ions can slide past each other, while the delocalized electrons continue to hold the structure together. Metals are ductile, which means they can be drawn into wires for a similar reason. The bonding is not between just two atoms. Instead, metallic bonding is the attraction between many positive metal ions and a shared sea of delocalized electrons. Examples include copper, aluminum, and iron. So the takeaway is, metallic bonding is the attraction between metal cations and delocalized valence electrons. Lecture 13. Potential energy diagram. A potential energy diagram shows what happens as two atoms move closer together and form a bond. On the horizontal axis, we have internuclear distance. That means the distance between the two nuclei. On the vertical axis, we have potential energy. When the atoms are very far apart, there is almost no attraction between them, so the potential energy is close to zero. As the atoms move closer, attractive forces begin to lower the potential energy. This happens because the positive nucleus of one atom is attracted to the electrons of the other atom, As they get closer, the system becomes more stable. The curve goes down until it reaches a minimum point. That minimum point represents the most stable distance between the two atoms. This distance is called the bond length or equilibrium bond distance. But if the atoms get too close, repulsive forces become very strong. The nuclei repel each other, and the electrons also repel each other. That is why the curve rises sharply at very short distance. The bond energy is the energy needed to separate the bonded atoms back to a far distance. So the deeper the energy well, the more energy is needed to break the bond. The main idea is stable bonds form at the distance where potential energy is minimized. Lecture 14. Coulomb's law and attractive forces. Coulomb's law explains the strengths of electrostatic attraction between charged particles. In simple terms, attraction becomes stronger when charges are larger and distance is smaller. The relationship can be written as force is proportional to Q1 times Q2 over R squared. Here, Q1 and Q2 represent the charges. The letter R represents the distance between the charged particles. So there are two big factors. First, charge. Larger charges create stronger attractions. For example, magnesium 2+ and oxide 2- have stronger attraction than sodium plus and chloride minus because the charges are larger. Second, distance. Shorter distance creates stronger attraction. If two ions are closer together, the attractive force between them is stronger. If the ions are farther apart, the attraction is weaker. This is why ionic radius matters. Smaller ions can get closer together, so they often have stronger attractions. Stronger attraction can lead to larger lattice energy and higher bond energy. So Coulomb's law helps us connect charge, distance, and bond strength. The main takeaway is attractive force increases when ionic charges are larger and the distance between ions is smaller.